Click the bell icon to get latest videos from Ekeeda.
Hello friends, in the previous topic we have discussed about what are the complex ions and what are the coordination compounds. And now in this topic let me explain you what are the characteristics of the coordination compounds and the complex ion. So what are those? Let me talk about that in this topic. So friends, here we are going to talk about the characteristic of the complex ions. So starting with the first point, that is generally a transition metal ion is the central metal ion in a complex. We understand that is to form a complex, the central metal ion should be surrounded by the ligands, but the central metal ion is usually a transition metal. The reason behind that is we understand that is the D block elements. For example, if we talk about that is iron, we talk about cobalt. So these are the certain D block elements that has various, or we could say variable oxidation state. And that's the reason that it could have that is unpaired electrons, and it would occupy many ligands to have the lone pair of electron in their orbital, and that makes the transition metal to have a better complex compared to that of the other one. So in that case, this is the main criteria, and this is the general characteristic that why the transition metals are basically forming a stable complex. So this was the first point. And talking about the other point, that is it is related to the coordination compound. That is, if we talk about the charge radius ratio, then we could find that is the D block elements, that is the transition metals, they have the higher magnitude of the charge ratio. So talking about the charge radius ratio, we could find that is the transition metals have a higher magnitude of the charge radius ratio, and that fulfills the criteria that why transition metal they form complex. So this was the first point, and now let me discuss about the next one. That is, an ion loses its individual property and acquires the property of the complex ion which it forms. For example, let me talk about that is Fe2 plus ion. Suppose if Fe2 plus ion is not forming a complex, then obviously suppose if it reacts with the base like NaOH, then it would form a PPT. But what if it forms a complex? So this is what I am going to talk about with the help of an example. So now let me give this example. So friends, now let me talk about the example where Fe2 plus ion, that is what we have to detect, and how we can detect it by reacting it with that is NaOH. So it could be found that is whenever the Fe2 plus ion it is reacted with NaOH or a base, we could find that the product form is FeOH twice. So here we have to balance this stoichiometry. So let me talk about this one. So this is the product, that is what we have got, and this product that is what we have got is nothing but a precipitate. So now let me take the example like Fe2 plus ion. Suppose if Fe2 plus ion is reacted with 2 moles of NaOH, and the product that is formed is that is FeOH twice. So the product that is formed is nothing but a PPT, that is a precipitate. So here basically we can find the Fe2 plus ion that has been present in a solution by reacting it with NaOH, and that is how basically the Fe2 plus shows its identity. But suppose if the Fe2 plus ion is in a complex, or it forms a complex like this one, where Fe2 plus ion is surrounded by that is cyanide group, the overall complex will have a charge of 4 minus. So to stabilize that, let me introduce this example. So this is the complex, that is what I have mentioned over here. But suppose if this complex it dissociates, it will dissociate into that is 4 mole of K plus ion along with that of FeCN, that is 6 cyanide ligands. They are surrounding the Fe, and the overall charge here it is found to be 4 plus. So here we could find that is Fe2 plus ion it participates the reaction with NaOH, and that is how basically it forms a precipitate. But here Fe is protected by the cyanide ligands, and that is how this will never get dissociated, and it will never form that is Fe2 plus ion. And that is how basically this will never reveal its identity. And obviously we could find that is the identity of Fe2 plus is different in NaOH, and in this case it is different. So therefore the property of Fe it changes. And suppose if this complex, suppose if I'm talking about the complex like K4 Fe cyanide 6. And suppose if it is treated with copper sulfate like CuSO4. So the complex that has been formed over here, that is, we could get Cu twice, Fe Cn6 plus K2SO4. So here basically we have to, that is, balance the reaction. So here I am balancing the reaction. So this is a complex, that is what we have got over here, but this is a brown color PPT which shows that Fe never dissociates from the cyanide ions, and that is how basically it has a different identity when a metal is forming a complex. So this was revealing the second point, and now let me discuss about the next point. So talking about the next point, that is, the complex ion can dissociate to slightly extent in the solution, however it retains its identity. For example, as we have discussed earlier in the second point, that is, whenever a metal ion is forming a complex, that is with the ligands, we could find that is it will never lose its identity. But if we talk about the complex, whenever a complex ion is able to dissociate in water or in any kind of solvent, it will never dissociate completely. It will dissociate till a particular extent, and even that less extent. So for example, if I'm talking about, that is, suppose if Fe2 plus ion is surrounded by, that is, cyanide molecules or cyanide ligands, so it will not dissociate that much compared to that of the Fe2 plus ion is surrounded by, that is, thiocyanide group. The reason behind that is Cn minus ions or Cn minus ligands, they are strong field ligands, and obviously they will form a strong interaction with the Fe, and that is how basically the dissociation is slightly less compared to that of the dissociation of Fe2 plus ion with that of the thiocyanide ligands. So this is what it depends upon. And now let me talk about the next one, that is, the strength of the bond between the central metal and the ligand determines the degree of dissociation. We understand that is ligands are of two types, that is a strong field ligand and a weak field ligand. So those ligands which have a strong interaction with the metal so that they would dissociate that much, those are known as strong field ligands, and they have a strong bonding with the metals. Those ligands, they form strong bonding with the ligands. And talking about the other ligands, that is the weak field ligand, they do form, that is, a coordination bond by donating the lone pair of electron, but they won't be that much strong compared to that of the previous one. So it depends upon the strength between the metal ion and the ligands. So talking about the next point, that is, the algebraic sum of the charges of the constituent ions is the net charge of the complex ion. Let me explain you with the help of an example. Suppose if I'm talking about, that is, ferrocyanide complex or ferrocyanide ions. So in that case, suppose if the Fe is surrounded by 6 cyanide ligands. So in that case, the overall complex, it has been found to have a charge of 4 minus. The reason behind that is, here basically the Fe or the iron has a charge of +2. While talking about the cyanide, each cyanide has a charge of -1. So thereby the overall charge, that is what we could get, is -4. So this is nothing but the fifth point, that is what I was discussing. So this all are the characteristic of the complex ion, that is what I have discussed, and that's it. So thank you friends for watching this video. I hope you have understood this video very clearly, and I hope I'll see you next time. Till then, don't forget to subscribe Ekeeda channel. Thank you so much.